Yes. Where were we? We were somewhere in the infinite.
But the infinite is very big.
Before the infinite, I think you want to do subtracting with exploding dots?
Are you ready for explosion this early in the morning? Because
explosions?
Your job, when we have an exploding dot, you go or louder or quieter as you choose. Exploding dots is a way of doing addition, subtraction, multiplication.
It's harder with multiplication, but
it's noisier with multiplication because you have many dots. So shall we do some addition?
Give us two numbers to add. 374 columns. And?
Much nicer.
So modest. Big.
Bigger?
121? 11 squared? Okay, 121. I'll draw columns for you.
Draw good columns.
I will draw good columns. Do we need any more? Well, I guess so. Who knows?
This is something that children love to do because it has noises to make. And everybody is waiting for the chance to make the noise. So we say, we have 374 will be 300s. And 4. I make mine in a neat box. He makes his all over the place. That's, girls are neat, boys are messy. And you tell me, 121, what do I put here? See, you're very good children. And the 2 goes here. And the 1 goes there. And the question is, how many do we have? Notice, children, all you have to do is count. And you're good at counting.
1, 2, 3, 4, 5.
Perfect.
Wonderful.
Harder.
1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4.
Too easy. No carrying.
But what
No exploding.
big numbers. And children love big numbers. Big numbers are their dangerous friends. So you say, how many cookies do you want? 4,300,000. That's worth doing.
Or yesterday, when Marina suggested that the dancer would end at minus 100. Wonderful. May I change? I want to have some explosions.
Yeah. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can I put a 12 here? No. What am I going to do? No, we don't give up that easily. We have 12. What's the biggest we could put here? 9. So what am I going to do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, 12 is 10 and 2. So I put a 2
You
there.
have to have them explode first. You have to have them disappear.
You want to make them disappear?
Yeah.
Okay.
Yeah. What about this one and this one? It's 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How about those? 1, 2, 3. Wait. 1, 2, 3, 4.
It's very early in
6.
the morning.
Yeah. 1, 2, 3, 4, 5, 6, 7. How did I do this?
It's a nice design.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
You have to understand, mathematicians run on coffee. If you don't have any coffee, it's hopeless. And he didn't have any coffee this morning.
Oh, yes. Now that they've exploded, what happens? There or there? Why?
Because it has less.
Okay.
It's very democratic. So what do we have here? And what do we have here? And
I think that's right.
4 and 1 is 5, yes. 7 and 5 is 12. And what children in America say is, put down the 2, carry the 1. I'm sure it's the same thing in every language. You put down and you carry. And so we get 525.
So it's so straightforward, so intuitively simple. Once you know it for life. Addition, what could be easier?
The only time we had trouble with children doing this was when we were teaching in Germany, and we said, and when 2 dots come together, they explode, and the children looked at their teacher, and they looked the other side of the room, and they said, pow. So I think your children will be a little more exuberant.
Subtraction. What do you suggest? Same thing. Give us a problem. Give us a number. A number.
475.
Wait, let me just write it down. 475.
Oh, you have it, so I don't have to.
Yep.
How many hundreds? See how hard this is? This is advanced math.
Well, you're so orderly.
I'm a girl. How many tens?
I want to do the 5s.
Oh!
What do you want to subtract, take away? 6,094. Beautiful. It has a 0 in it. How do we write it? What do we do?
Because if it's a solid dot, it's real and it's there and we keep it. But if it's a negative dot, what does it do? This is very ugly.
Invent
The
something.
negative dots do what to the positive dots?
Make them go away. They
Many
eat them
children
up.
say they eat them up.
So,
Life should be a struggle for numbers.
make them hollow. Make them empty.
Because they're hungry. 6,000.
No hundreds.
9 tens.
And 4 ones. Now we need a new rule. We need to know how the hollow dots and the solid dots interact. What do you think? Think subtraction in your mind, translate it, not into Portuguese, translate it into how dots, solid and hollow, behave.
110 explode to 900.
Good. Say that again.
1,000 explode to 900.
Okay.
10 sorry.
Complicated, might well work. Just in the ones column, I've got 5 solids, 4 hollows.
Darwin says nature is red in tooth and claw. Animals eat other animals.
This is ready to eat.
Zeros eat numbers. Zeros are very dangerous.
So this hollow dot eats one of the solid dots. I don't know which. It's a matter of what the landscape is like and how the battle plans have been drawn up. But perhaps...
I think these guys are in danger.
Yes, yes. This one eats up this one. And they cancel each other out. The solid disappears, the hollow disappears. Do you think 4 or 5-year-olds or 6-year-olds would understand that? It might be a little hard the first time you do it, that both of the dots disappear. That they cancel, I think perhaps the word cancel is good. They cancel each other out. They, as you said, one eats the other.
I think eating is a very good image for mathematics.
This is in danger. Go.
Are you worried about those 3? Yeah, it's going to be awful. Don't look. This one comes up and eats that one. And this one down here is now very vicious. Oh!
And we have the one survivor coming back from the Battle of Marathon with news that everyone has been killed except he who has come home. So far, so good. We've almost got the answer. We're part of the way toward the answer.
Okay. Now you do it. Start destroying these. Now, What do you need to do in order to know how to destroy dots? Almost nothing. You can see a dot, and you can see a hole, and the hole comes and eats the dot. You notice the required sophistication in mathematics is almost nothing. And I've never known a child who didn't catch on to this instantly, especially if you make the noise. And that, I think making the noise puts it in your head. So you say, what is subtraction? It's gobbling it up.
You notice we might have a slight problem here. 7 solid, 7 hollow. Oh, and 2 others. We'll take care of that when we come to it. 7 of the hollow. Eat up, cancel, destroy 7 of the solid.
You can make the vocabulary much more peaceful. If you don't want your children to be destroying things, they can walk away together hand in hand.
But now what? What do you do with that? Is the answer going to be question mark minus 2, 1? Is that a normal number? No. So we've got a slight problem here. Solve it for us. Help.
Take off a dot of hundreds and put it in tens.
Terrific. Take one of the hundreds and move it over. Do the reverse of what we did yesterday and put.
Here.
So those are supposed to be solid. Wonderful. That will be the hardest thing for the children to get, but they'll like it. It's going backward in the game. Now we can go to work. Good.
What happens here? How many do we now have? 10. And how many people to eat up the 10? 2. So we have. You're very quiet and frightened.
Be noisy children.
It's not scary. If you have how many? 3, 6, 9, 10, and you have 2 gobblers who are going to eat them, how many do they eat? 2. They're very polite. Each eats 1.
And so,
How many do we have here?
by the way, looks good so far. Now it's plain sailing.
How many hundreds do we have? 3. Everybody in the whole room says 3. Nobody's frightened? Nothing scary is happening? No tears? Great. A math class with no tears? That's wonderful. So how many hundreds? We say 1, 2, 3. Not hard. And how many thousands do we have?
Oh, we have 6 eaters of thousands.
Uh-oh.
Uh-oh. What do we do? Do what we did before. Move one of the thousands to the hundreds. Now you go back to yesterday. We have 13 here.
No, they are both.
What happens?
In the thousand it was a halo dot, and it become in the hundreds a full dot. I don't get it.
Oh, empty dots and full dots.
Oh, you're saying I should have written hollow dots here. Is that what you're saying? Why not?
How many?
Okay. So now what?
Have we hit a problem? Has mathematics died?
Yes. So tell me what to do.
3 of the holes, each 3 of the dots.
Great. Now what? I have a suggestion. We're at a very interesting point. You've done this extremely well. Could you write it down? Could you write down where we are? Keeping this calculation also, so you know you're allowed to use your calculator if in doubt to figure out what the answer should be. Leave it at this point. Think about it, each of you. And let's pick it up here tomorrow morning. So this is really a math circle. We're not doing it for you. You're doing it for one another. You're thinking about it all together. We're at a very interesting point. Somehow, you'll know the answer you're aiming for if you do it the old-fashioned way. And you'll also be able to decide whether you might not want to use exploding dots for teaching subtraction if you think it's going to be too hard, too complicated. My personal feeling is, in the end, the kids like it. They have to do some extra thinking along the way, as you already have. But let's pick up this problem at this point, at this time tomorrow, one freckle past wrist. Okay. Okay, let's stop here.
I will erase.
And let's go back to the infinite. Oh, did I erase it too soon? Oh, it was. The blackboard has a memory.
You can also look at this, and you can have a history and economics lesson at the same time as a math lesson. You have 475, and you need 6,094. What has happened?
Someone asked us yesterday, how on earth do I explain what subtraction is? And there are different ways of thinking about it. Temperature going down below zero, but not in most of Brazil. Owing money. Things that you don't have, but that you need or would like to have. What is missing, what is absent, always harder to think about than what you do have. Okay,
But philosophically, it's very important to realize that what you don't have is as important as what you do have. And you can say, what do we need? And that's something children understand. I need more transformer dolls. I need more cookies. And then you have the start of an interesting conversation, which is a nice break in a math class.
What I need right now, Rogerio is some chalk, which is sitting behind you. It was -1 chalk. Thank you very much.
Now what?
I'll do the infinite. Stick it.
Yeah.
So yesterday, what you did was to find, discover, invent a way of showing that there are exactly as many rational numbers, fractions, between 0 and infinity, positive rational numbers, as there are counting numbers. Not more, as you might think at first. And you did it by this weaving diagram, Diego's squares. And there are exactly as many. It's so strange that there are no more. But, of course, we've left out all the negative rational numbers, -13/18. What if you take not only all positive rationals,
Would you like me to write?
oh yes, please. So it'll be actually legible. Not only all of those, but the whole left-hand part of the blackboard. -1/1, -2/1, -1/2, -1/3, and so on, forever. Now, what are there more of? All the rationals, except for 0, all of the rationals, positive and negative, or the counting numbers? Or is there a way of matching everything up with the counting numbers? The beautiful part of your work now is that you have almost nothing to do. You did the hard work yesterday. If you just think about it for a minute. Say it again.
The
Evens and odds. You want to match up the positive fractions with odds and the negative fractions with, we're done.
Could you say that again? I was not listening.
You take an idea from yesterday. This is the wonderful thing about mathematics, that each part of it helps another part once you see or invent the connection. We knew from yesterday that there are as many evens as there are odds, as there are counting numbers altogether. Break up the counting numbers into 2 piles, evens and odds. Match up the odds with the positive rationals. Match up the negative rationals with the evens, and we're done. Except that just like yesterday, I left out a number here. I left out the key number, 0. Now what? Yes?
If the naturals match the rationals, you can also match these to the integers. And then you know the integers already match the naturals to begin with.
That sounds just right. I didn't get every word of it. Could you say it one more time? What did you have?
No.
Well, we do know that the naturals match with the rationals.
Yes.
And we do know that they also match with the integers. So you can match this set to the integers more easily now, right? You can just match the ones that were matched before.
That's very nice. You're taking another idea from yesterday. It was the last idea, or next to last idea of yesterday. We know that the natural numbers match up with all the integers, including 0. Take all the integers, including 0, and match them up with all the rationals, including 0. We've already done the work. Terrific.
But we do need to know how we should travel around this.
Yes, if you want a picture of how to travel, well, of course, there are going to be an infinite number of possible pictures. You could, if you'd like, start at
But
0.
one thing you can't do is you can't start over here. Why not? What's over here? Infinity. It's a bad place to start.
There's no longer a corner of the room to start cleaning from. So start anywhere. Start there. Well, it seems a perverse place to start, but start anywhere. Start there. It's more natural. And start weaving in Diego squares, but now larger. Well, it's going to be a funny pattern, rather like what we were doing at the end of yesterday, going through those 5 by 5 squares. Make yourself some pattern that's pleasing to you and that you feel you have control over, weaving backward and forward, always picking up new things on each sweep. And it's perfectly fine, of course, to start anywhere. It's just more intuitive, more natural to start, let's say, at 0 or 1 over 1 or negative 1 over 1. Now comes a huge jump. Do you know how to turn a rational number into a decimal? What I mean,
Should I write a half and 0.5?
make it 1/7. Do you know how to turn 1/7 into a decimal without using your calculator?
Nobody knows that.
Is there a decimal that corresponds to it? There is. And a decimal is just different powers of 10 in each place. Do you all
Can I
agree that
say
there's a
that-
0 here?
That a half equals 0.5 is very nice and comfortable. We're not scared.
Only one, yes, 0.50. Oh, in fact, 0.500. Oh, I'm sorry, I meant 0.5000. But you know that I should have meant 0.50000. Usually you write this as 0.50 with a bar over the 0 to mean it's 0 from there to infinity. Okay.
But we're very busy and we're not going to draw all the zeros.
By the way, 1/2 is not equal to 0.5000001000. That is not 1/2. It's slightly larger. Yes, you're happy with that. Okay.
I wouldn't say happy. I'm not seeing many smiles. It's okay to be happy in math class.
How do you find out, without your calculator, what the decimal form of 1/7 is? This, by the way, is beautiful and fascinating in itself, and your children will need to know this, and it's a very good way of teaching what division is and how division works, because you're saying you want to divide 1 into 7 parts.
This leads to a very good conversation because children usually see numbers as solid blocks. And you say, what is half of a solid block? And they think, this is madness. I've had it with math. I'm going to go study philosophy, something really easy.
And yet there is a way of finding out how many tenths will be involved in a 7th, how many hundredths, how many thousandths, and so on. If you have an idea of how this works, don't say it, but just raise a hand so we know how many people feel comfortable with this. Not too many hands raised.
Very sensible people. Put your hand a little bit up.
My guess is that we use a different way of picturing this in America from what you do here. I don't know how you picture it here. What we do is this. We say, put the 1 inside a house, put 7 at the door, and put more rooms on the house. I don't know how many I'm going to need. Just let them go on for a while. Thank you. So this is a door and a roof. I'm now, I hope, using the language that children would feel comfortable with. And you ask the question, which is a strange, dumb question. How many times does 7 fit into 1? How many in 1? If you're wondering why we're doing this, it's because we're on the verge of talking about a larger size of infinity. But we're about 20 minutes away from it.
So if you're scared by a large size of infinity, stay for 15 minutes and then run out of the room.
Are you happy, or at least do you agree, that there are no 7s in 1? Well, how many 7s are there in 10? 1. And 1 times 7 is 7. Take that away from the 10 and see what's left. Now, what's going to be important right now is noticing what these remainders are. A remainder of 3. Bring down the next empty room and start again. Ask how many 7s fit inside 30, maybe all the way up to 30, but at least not beyond 30. 4. So I put the 4 for the how many up here. I do 4 times 7, 28 here. Subtract and look at the remainder. The remainder here was 3. The remainder here is 2.
It's beginning to look interesting.
So far, the decimal form of 1/7 is 0.14. Bring down the next empty room. Ask the same question. What's the most number of 7s you can fit inside 20? 2. 7 times 2 is 14. Take that away. See what's left. A new, different remainder. 3, 2, 6. Bring down the next empty room.
Getting harder.
How many 7s fit into 6? 8. Subtract.
A good thing about this question is, as you can see, it's going to take a long time. But it's also looking as if something interesting might happen. And it's a chance to do a long, long division problem with people still interested. It's not the, oh, here we go, we're going to spend the rest of the day, put down, carry, all of those awful things. You keep thinking something's going to happen. This has to have an interesting ending. And amazingly, it has. This really is a good story.
Because the remainders, that's what matters. The remainders have been 3, 2, 6, 4. They're all different. 2, 3, 4, 6. Will they always be different? Will the remainders keep changing to new numbers? Why not?
So just 9 numbers to be there.
I agree that there's at most 9 options. I think there are fewer. When you're dividing by 7, how much can be left over? How many different possible remainders are there? Aha! Great. We must be closing in on this. 5. Subtract a new remainder. 2, 3, 4, 5,
6.
6. Now watch. 7 times what fits into 50?
7.
I'm going to move that over to here. What's the remainder? 1. 1. We're back to where we started. What does this have to be now from here on? It has to repeat. It has to be 1, 4, 2, 8, 5, 7. 1, 4, 2. The decimal equivalent, the decimal form of the fraction 1/7 has to have a repeating period of at most 6, because there are at most 6 possible remainders. It's going to be 1, 4, 2, 8, 5, 7, bar, repeating. And in fact, with any fraction you name, too easy.
Oh.
This will have some sort of decimal form, which will repeat at the very most after 318 places. It might repeat sooner. 1/3 has a decimal form which repeats at most after 2 places, but in fact, it repeats after 1 place. So it's the very most number of remainders you can have. Every fraction must have a repeating decimal form. That turns out to be a very profound fact, because it means that you, right now, might be able to make a decimal which does not correspond to a fraction. There might be more decimals than there are fractions, or at least different decimals from fractions. If every fraction has a repeating decimal, and it does, every fraction, every rational.
Shall I write that?
Yes, please. Every rational number. Legible?
This is elementary school teachers write so you can understand it. University professors write so they can understand it. Every decimal, yes?
Has a repeating, I'm sorry, every fraction, every rational. Here. Has a repeating decimal form, has the form of a repeating decimal. So could you now please make for me, for one another, for us, a decimal which is guaranteed not to repeat? Fantastic. What did you say after the 9? Ah, so that's repeated. Oh, but that's prevented the repetition. Well, but maybe this will repeat after I get to 1, 9? No, it's the 2, but now the 0 after it. This will never repeat. This must not be a fraction. It's a decimal, It's a small decimal. It's somewhere between a tenth and an eighth. It's in between them, but it's not itself a rational number. When we're talking with very young children about numbers between numbers, as we did yesterday, they have no idea how many numbers there are between numbers. Not only between 1/8 and 0 is there 1/9, as Rebecca suggested, there's also monstrous decimal numbers which are not rationals. And they're not going to hear about that, I imagine, for years. So, here's the question. Are there more decimals, rational and irrational, rational and not rational? Are there more decimals than there are counting numbers? Or are there, again, exactly as many? And we just have to find a way of counting. That's the question. Are you ready to attack the answer? This is going to be huge. The great Greek playwright, Sophocles, said, "No great thing comes without a curse." This is great. It has a curse. It's very hard. What does hard mean? You're certainly going to be able to think about it. You're going to understand it. By this evening, when you think it over, you'll have gotten it. But it's going to be hard along the way. Sorry. What we're going to prove is that there are more decimals than there are counting numbers. You can't count them. It's a larger infinity. You can't match them
Did you hear him say that? It's a larger infinity? How could it be larger than infinity? My head hurts. I want to go home. I think I hear my mother calling me. This is a bad moment, and it leads to wonderful things. And that is the blessing and the curse of mathematics, which is it is always interesting, it's always perplexing, and it's always harder than you think it's going to be.
And dangerous, and then in the end, glorious. How do you show that two sets are the same size? What you did yesterday and this morning. You match them up. You match the two sets up. You make the people sit down in the chairs until there are no people left standing and there are no chairs empty. You matched up all the counting numbers, 1, 2, 3, 4, 5, and so on, with all the odd numbers, with all the integers, with all the positive rationals, with all the positive and negative rationals.
With all the multiples of 4,721.
That's right.
But we didn't make you do it.
But how do you show that two sets are not the same size? This is the big idea. It's one of the great inventions of the human mind, of your minds, the minds of our species. You assume that there is a one-to-one matchup and get a contradiction. Proof by contradiction. Assume that there are exactly as many counting numbers as there are decimals, and then show that you were wrong. Somehow, something is wrong. Somehow, you've left out one. Well, then you must have been wrong in thinking they matched up. It's a hard idea to keep in mind, but it's worth it. So I'm going to assume a one-to-one matchup of counting numbers and decimals. Oh, good. Neither smiling nor frowning.
That is terror.
Here are all the counting numbers going on just forever. There are as many of them.
Just forever? No further than forever?
The floor
Okay.
is forever. All the counting numbers. They are your friends. You know them. We've been thinking about nothing but them for 2 days. Let's be modest. Let's just look at all the decimals between 0 and 1.
How many decimals are there between 0 and 1? An infinite number. So this did not make it noticeably easier.
We're going to try to match them all up with the counting numbers. Assume we can match them up and see that something went wrong. Each of these decimals begins 0 point. Yes? The very first one on the list begins 0 point. The second one, the third, the fourth, they all begin 0 point something. I don't know how you want to make your list. I don't know how I want to make mine. This proof is supposed to work for any possible list. So we can't say, well, let the first one be 0.100 something. I don't know. I don't know what's going to be in the first decimal place of the first number on the list. But I do know this. It will either be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. There are no other possibilities. Is that okay? So this is either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. There are other decimal places here, of course. This goes on forever to the right. Each one of these decimal places is one of those numbers. They might all be zeros. They might all be fives. I don't know. They might alternate. They might be 142,857, 142,857, 1/7. They might be 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2. Likewise, the second number on the list. Whatever I said about the first applies to the second. Each decimal place is one of those 10 numbers. Now, please say right now if everything is okay so far. You may be worried about the future. You should be.
It's very nice looking out at you and seeing the heads nodding. And they're nodding
Cautious.
very little nods. So, but don't worry, it doesn't hurt. We've done the hard part already with the idea that a number is an infinite number of decimal places going on out in the street, being run over by cars, ending up in the lake. It's huge.
This is a little bit like a speech by a politician. They get you to agree to obvious conditions, and in the end, you turned out having agreed to having a dictatorship. We all agree each of these blanks, anywhere along the way, each of these blanks is filled by one of the 10 numbers, 0 through 9.
To make it more obvious, make a different number of blanks for different numbers. It's not, they all go the same number.
You mean like this?
Yeah,
Yeah.
yeah. I mean, this is very messy on the edge. Like, there's always, in every room there is somebody who knows the decimal places of 1/7. Do we have somebody who knows the decimal places of 1/7?
142,857, 142,857.
There, you have something to take home to your school.
Okay, let me just review where we are. We're going to assume that you can list all the decimals between 0 and 1.
Actually, this is very nice of us. We could have asked you to list all the decimals between 0 and infinity.
But no, more modest. We're going to show that there are more decimals between 0 and 1 than there are counting numbers. Assume there are exactly as many. Assume you can make a one-to-one matchup somehow. Do you agree that what goes in the first place of the first number is 5 or not? Well, that was easy. Easy
Oh, no,
and
you
crucial.
didn't get many agreements.
Okay, let's
If
say
you
again.
look at faces,
This
the
might have-
faces are saying, is this where the man takes my money and runs away? Yes.
If this first number on our list was 1/7, there would have been a 1 here, not a 5. If this first number on the list had been 1/2, there would have been a 5 here. But I don't know. I don't know what the first number on the list is. I'm just assuming that there is a first number on the list, that we've made the list somehow. No number has appeared, no decimal has appeared twice. Each decimal between 0 and 1 has appeared once. We've got them all. So that first number is a 5 or it isn't. First, actually, Ellen, you should write this. The first decimal place of the first number on the list is 5 or it isn't. Any guesses about what the next idea is? Think back to the end of yesterday and the way you went through counting all the rationals. You couldn't go in a straight line because then you'd never get to the next row. You couldn't go in a straight line down because you'd never get to the next column. You had to zigzag. We now know something very innocent. The first decimal place of the first number on the supposed list is a 5, or it isn't. The second decimal place of the second number on the list is a 5, or it isn't. The third decimal place of the third number on the list is a 5, or it isn't.
Now, at this point, I agree it's either a 5 or it isn't. And I see we're moving down on a diagonal, which looks as if we know something about what we're doing. It's not just random. But I have no idea why we're doing this. I have no idea why we're using 5. I have no idea what's happening before the number we've circled. And I would like a clearer explanation of what we're doing.
I'm not sure yet, but I do know this, that what we're doing is recreating the greatest work of art of the 19th century. Better, more beautiful, more profound than a Beethoven quartet, than a painting by Monet, than your favorite novel of the 19th century. Any work of art you name, this is more profound, more outrageous, more spectacular, more disturbing. And yet all we're doing is looking at the first decimal place of the first number on our supposed list, the second of the second, the third of the third, the fourth of the fourth, the fifth of the fifth, and so on this diagonal forever. Now, each one we say,
Do we agree we could put a number, any number we wanted, in the first place of the first number? Is it open to democracy? As we can say, I would like to put a 5 there. And you say, nah, I'd like to put a 3 in the next row. And we say, go ahead. As we say in America, be my guest.
we end up, supposedly, with a list of all the rationals between 0 and 1, all the decimals, rational and not rational, between 0 and 1, each one appearing once and only once.
Is each of those numbers bigger than 0?
Well, of course, one of them might have been 0, or you might
Or
want to leave
zero-
off that left-hand endpoint. I don't
Okay.
care. It doesn't matter. So each of the numbers is either 0 or it isn't. This might be all zeros. But anyway, that first number is a 5 or it isn't. The second decimal place of the second number is a 5 or it isn't. The nth decimal place of the nth number on the list is a 5 or it isn't. A very simple criterion.
At this moment, my head begins to hurt. Anybody else's head hurting? No. Great. Okay, we have a slightly painful head in the back. Yeah, can you explain what you're actually
Okay.
doing?
Huge steps of thought. First, suppose there are exactly as many decimals between 0 and 1 as there are counting numbers, which means we can count them, we can list them, we can have them sit down in chairs with numbers on them. These are the chairs. This is the list of all the counting numbers. It doesn't stop. It goes on forever. To each counting number, we match up a decimal between 0 and 1. We never put the same one down twice. And we say,
That's a very important idea, that diagonal line.
is going through different numbers, different decimals.
Because if this one agrees with this one in this decimal place, they might be the same. But if we say this is the line that's going to be differentiating, they can't have the same.
What if, for example, the first number on the list had been the decimal form of 1/7? What if the second number had been 1/2? What if the third number had been,
What a-
I don't
what a
know,
third?
1/8? What if the next one had been all 5s? What if this had been 6, 9, 7? I'm making this up as I go along. 2, 5, 3, 8, and so on. All different numbers. And the person who has made this list says, I've got every single decimal between 0 and 1 on there. None repeated. I've counted them all. I've matched them up with the counting numbers. Big, next, and last idea. We are going to make up a number which is not on that list. A perfectly good decimal number between 0 and 1, which we forgot, even though we claimed the list was complete. So our number, our decimal, is going to begin 0 point, because it's a decimal between 0 and 1. What's in the first decimal place of our number? Well, you look at this list, you look at this diagonal. If the first number in the first decimal place was not a 5, put a 5 in the first decimal place of our number.
So is our new number the same as the first number? Absolutely not.
It differs at least in the first decimal place. Of course, it might have turned out to be the second or the fourth or some other number. The second decimal place of our number, you look at the second decimal place of the second number on the list. If it wasn't a 5, and it isn't here, put a 5 in the second decimal place of our number. Look at the third decimal place of the third number on the list. If it wasn't a 5, put a 5 in ours. But if it was a 5, put a 6 in ours. So
By the
far,
way, there's nothing magical about it being 5 or 6.
Yes, I just
You-
chose two numbers.
If your favorite digit is 7, feel free to use 7.
This number that we're making, our number, can't be the first number on the list. It differs from it at least in the first decimal place. It can't be the second number on the list. It differs from it at least in the second decimal place. It can't be the third number on the list, and so on. Make our number out of 5s and 6s. According to that rule, according to that recipe, look to see what the number on the diagonal was of the place we're interested in and be contrary. Put a 5 if it wasn't a 5, put a 6 if it was a 5. We end up with a perfectly good decimal, somewhere beyond, a little bit beyond a half. It's between, what, 5/11ths and 2/3. It's made up of all 5s and 6s. It's not on the list. It's not there. It's nowhere on the list. But it's a perfectly good decimal. If you say, well, stick it at the bottom of the list, there is no bottom of the list. The list was finished before we began making our number. The list was supposedly complete. The list supposedly had every decimal between 0 and 1, but it didn't have that one. And in fact, there are a lot more it's not going to have, but at least it's missing one number. There are more decimals between 0 and 1 than there are counting numbers. It's a larger infinity. Mind-boggling though that is, the counting numbers, it's a tiny infinity. It just goes on forever.
Now, at this point, you should be feeling very floaty, because the thing that everybody says about arithmetic is it's completely boringly understandable. And you say, what is 3 plus 5? 3 plus 5 is 8. It will always be 8. It's not like poetry. You can't say, it's such a beautiful day that 3 plus 5 will be 17. No, it's going to be boring arithmetic with the same answer. As somebody said, math is awful because you're either right or wrong, whereas poetry, anything can be happening. But if you look at this is getting close to poetry. This is getting close to being something which you can imagine. How long is this list? It's infinite. What does infinite mean? No, there is no finis. There is no end. It goes on forever. So you're talking about a possibility which is greater than anything which can be in this world, greater than can be in this universe. This is the sort of thing, if you're lying in bed at night before you go to sleep and you start to think about how far away is infinity, you better get up and go have a drink of water and go back to bed, because you will not sleep if you don't break the thought.
Plus ultra. Plus ultra. It goes on forever. Yes.
If between 0 and 1 we have numbers that are going forever, how do I know that get to 1? Because if it's forever, you shouldn't get anywhere. Or somewhere, but you cannot have an end.
Good question. Just between 0 and 1, we can do the same thing between 1 and 2 and between 18 and 19. Just between 0 and 1. We thought we had listed every single one of the decimals in here. Those that corresponded to rational numbers, those that didn't correspond to rational numbers. We did our very best by not specifying how to make the list. Just say, look, make the list any way you want. But imagine, pretend, think that you've got every single one listed. Ah, here's one you forgot. No matter how you made your list, no matter how you made it, by diagonalizing through it. The great idea in this mathematics is the idea behind much of Japanese art, Japanese painting, moving on the diagonal, not moving in straight lines, but moving on slant lines. Moving on the diagonal, you find a number you had forgotten.
So you say, our number here can't be the same as a number here because this starts 1, 4, 2. This one may start 1, but it won't start 4, 2. Or even if it starts 1, 4, 2, it'll be different there.
And yet our number differs from it in the first decimal place. It differs from every number at least in one decimal place. Maybe elsewhere, I don't know. But if two decimals differ in at least one decimal place, they're different.
Makes your head hurt. That's
Beethoven's Waldstein Sonata, the piano sonata, has in it a moment when there's a cycle of fifths, when he modulates up by fifths, and the dynamics become softer and softer as the spiraling up of fifths goes on forever. This really does go on forever. This is the piano sonata. This is the work of art that touches from our finite, immediate world beyond the infinity of the stars, which are only as many as there are counting numbers, and probably fewer, beyond the number of counting numbers. Our imaginations seem to have stopped with that many numbers, and now all of a sudden opened up to this new infinity. When the great German mathematician Hilbert in the 1920s said that Cantor, Georg Cantor, of whom we talked yesterday, the one who came up with this idea, came up with this proof, Hilbert said, Cantor has thrown open the doors of paradise to us, and no one shall close those doors. We are living in a world so infinitely vast that it's frightening or exhilarating, depending on your mood. I'm very sure you're feeling nervous, shaky about this in some or all of its parts. Think about it some more. Let's talk about it again tomorrow. We'll talk about an even larger size of infinity tomorrow. There are at least 3 sizes. I mean, 4. Well, I mean, there are really 5 sizes of infinity. Well, 6. I mean, the sizes of infinity themselves go up more than forever. You've just seen 2 of the smaller sizes. There's a lot we don't know about this. For example, we don't know if the size of the decimals, this new size of infinity, we don't know if it's the next size up after the counting numbers or not. We just don't know. Some people say we'll never know. Some people say, well, this is only, the end of July or beginning of August? Just wait till September of some year. But mathematics, we're out on the frontier. This is the Wild West.
But what makes it really exciting is that it starts with 1 + 1 = 2. And it goes on using the same kind of tools. To add 2 numbers together is something that you start doing when you're about 3 years old. But to add and add and add and add goes on to this possibility of, does it ever end? Do you have to stop adding? Obviously not. But we're standing at the edge of the universe and saying, take another step.
Plus ultra.
Where do you go?
A 1-sentence summary of what's happened today. There are only 2 ideas here. 1-to-1 matchup and proof by contradiction. 1-to-1 matchup is hard but relatively easy. Proof by contradiction is really something to get one's mind around. I think it's very hard I think it's almost impossible for 4 and 5-year-olds. We've done this with 8 and 9-year-olds, and they have gone out of the room like this, but they've come in the next day like this. Thanks a lot. To be continued tomorrow.